Hello everyone, let's start solving the first 5 organic questions of the JAM 2018 question paper, right. So let's start. The first question says the major product formed in the following reaction is. So we can see here what we have. Here we have a substituted chlorobenzene and we are reacting with sodamide. So if we see a chlorobenzene or any benzene which has a good leaving group and you have sodamide, the first thought which should come to your mind is it should go through benzene mechanism. Why? Because sodamide is a very powerful base, Na plus NH2 minus. So this will help to remove a proton from the neighboring carbon of the carbon containing chlorine, and then you get triple bond kind of benzene. This is what I am talking about. So that's what happens. So first NaNH2 reacts and then it takes away this proton, you get benzene. So generally what happens is when you have a benzene mechanism, if you don't have any other species, you have ammonia, this ammonia will attack either from here or from here, and then you get substituted aminobenzene, right. But here we can see on the neighboring to the benzene which is formed, because chlorine is neighboring to this alkyl part which has cyano at the last, and then when you remove the proton, the only proton available for removal is this one, and so you get a benzene, and then you still have NaNH2 because it's a very powerful base. It will remove another proton to create a powerful nucleophile. Now this proton is acidic to a certain extent. Why? Because if you remove this proton, the conjugate base formed is stable. That means after removal of proton it is still stable, so it does not mind being removed, and therefore this proton is acidic, and therefore this one removes the proton and you get negative charge, you get here which is stabilized like that. And so what happens, negative charge on carbon, it is a very powerful nucleophile because carbon is not at all electronegative, it cannot stabilize negative charge. So it will immediately go and attack wherever it is possible. Apart from that, because it is carbon which is not electronegative, its lobe is very large and therefore it acts as a very powerful nucleophile, right. So this will go and attack the benzene. So now the attack has to be at position 2, not at position 3, because position 3 it become very skewed, because you see this benzene ring, it is planar, it is 120 degrees, so it forms a ring. It is not possible for it to go attack this way, so it will attack at the position 2, or rather I would say alpha to the bond from where this attaches here. This goes and picks up proton from ammonia and you get this ring, and therefore the answer is option C. This is the product, right. Next question, the compound that contain most acidic hydrogen is. So I have to look at the hydrogens. So here the hydrogen is present on this carbon. So this carbon, you can see there is a double bond, that means one pi bond, right. One pi bond means one p orbital is there which is unhybridized, and other orbitals are hybridized. So that means it is sp2 hybridized and one orbital p orbital is unhybridized, which is forming pi bond. So this is sp2, this is sp because it has two p orbitals, two pi bonds, that means two unhybridized p orbital. So you know there is one s orbital, then there are three p orbitals, px, py and pz. So therefore since it needs two unhybridized p orbital, only s and p undergoes hybridization, and therefore it is sp hybridized orbital. Here also this carbon is sp2 hybridized and this carbon is sp hybridized, because this carbon has two pi bond and this carbon has only one pi bond. But we are interested only on the carbon on which hydrogen is there. So since hydrogen on the carbon, this is also sp2 hybridized. So this proton on the molecule C and this proton on the molecule A, both of them will have very similar acidity, though the first molecule is alkene and the molecule C, that is a allene. Allene, on the central carbon two pi bonds are there on the either side, right. And then this is alkane, so this proton is sp3 hybridized. So this is a very simple question. the proton which is on sp hybridized carbon is most acidic than the proton which is on sp2 than which is on sp3 hybridized. Why? Because this carbon is sp hybridized, you see. So here is the carbon and here is the hydrogen. So this bond, this orbital through which it is bonding with hydrogen, this is sp hybridized. So sp hybridized means if you see sp3, what is the s character? So you have to look how many total orbitals are there. Total there are 4, 1s and 3p. So 3 plus 1, 4. Out of that s is only 1. So 1 by 4 times 100 that gives you 25%, right? That gives you 25%. So 25% s character on the carbon which is sp3 hybridized, right? Whereas when it is sp2 hybridized like this or like this, you can see out of 3, one of them is s, so it has 33%, whereas when it is sp hybridized it is 25%. It is having 25% s, it is having 50% s character because 1s and 1p, so it is out of 2, 1 is s, so it is sp hybridized. So now what happens is, because it is sp hybridized, it has having 50% s character, maximum s character. Now s orbital has more penetrative effect than p orbital. What I am trying to say is, s orbital is closer to nucleus than p orbital, and because s orbital is closer to nucleus than p orbital, so this orbital will feel stronger attraction towards the nucleus. That means these electrons, these electrons in the orbital, these 2 electrons gets attracted toward this carbon more strongly than any other molecules which are shown. So what happens is, it means this carbon is more electronegative than any other carbon which has hydrogen, and because it is more electronegative, it will be able to stabilize negative charge more than others, and therefore it will be easier to remove this proton on alkyne than remove the proton from any other, and therefore B is the answer. Alkyne proton is most acidic compared to others. Now the C2 epimer of glucose. So let's first understand what is glucose. Glucose, you know, is the easiest molecule to remember. You have to make a cyclohexane ring and put oxygen on one of the positions. Then this is carbon 1 which has OH. Now this OH we have to draw wavy line because this OH can be on axial position or equatorial position. And then after that, it is very easy to draw glucose because all the OH are in equatorial position. So you can see here, this is carbon number 2. On carbon number 2, on the equatorial position OH is there, and axial position your hydrogen is there, right? Similarly, if you look at this position, at this carbon, again here, this is the equatorial position and this is the axial position. So as I said, glucose is very easy to remember. This OH will be again in the equatorial position and H will be in the axial position, right? Similarly, here again this is the equatorial position, this is the axial position. Because it is glucose, it is easy to remember, the bulky OH will be in equatorial position, which is sterically more stable, and hydrogen comes in the axial position. And on the last one, here axial position is again hydrogen and equatorial position is CH2OH, which is again in equatorial position. The bulky portion, bulky ones are in the equatorial position. That is why if you see, glucose is the most abundant sugar present in nature because it is most stable. So now what it says, C2 epimer. So what is an epimer? Epimer means there is change in stereochemistry at one of the carbon, right. See, glucose and all other of these, that is mannose, fructose, galactose, and glucose I am not very sure, I think it has one less carbon, but anyways, at least these three, they are diastereomers. That means for them at least in one carbon or two carbon there is change in stereochemistry. Epimer means only on one carbon there is change in stereochemistry, and when at position 2 if you have change of stereochemistry it is mannose. If at position 4 there is change in stereochemistry it is galactose. So here this is glucose, so mannose will be, instead of OH in equatorial position, H will be in equatorial position, and on axial position there will be OH. So the answer is very clearly mannose, whereas galactose is epimer position 4. And fructose is not a epimer because it's a different ring, that is a 5-membered ring which it forms. Here it is 6-membered ring which is the main conformer, right. So this is glucose and this is mannose. Next question is, somehow I find this answer, the only option which looked close to correct was C, but I do not think the options they have given is right, maybe printing mistake or something. Let us look at it, I will explain you what I am trying to say. So you are having this carbocation. So carbocation we have to look at the stability, which is most stable, right. So anything which is localized, anything which is charged is not stable, and if it is localized in one place it is more unstable, immediately it will be attacked by negative charge. But if this positive charge is delocalized, that means spread over long space. So what happens, the more it is spread, the less amount of positive charge density will be here. So negative will not be so much attracted to it, so it will be stable, right. So when you are having a isopropyl positive charge here and you are having benzene ring, so benzene ring will stabilized by resonance. You can see here, this will come here, this will attack here, and you get positive charge here. Similarly, yeah, I have drawn here, see it goes here to get a positive charge here, then this comes here, this comes here. So this positive charge is effectively spread between 1, 2, 3, 4 carbons. So this carbon only has 1/4 of positive charge, quite stable. Whereas if you look at this one, here it is being stabilized again by resonance, you are having positive charge here and here. So it is having like 0.5 positive charge. So both of them very stable. So in carbon number 1, in the molecule 1 and molecule 4, the stabilization is because of resonance, and resonance stabilization is much more stronger than your inductive effect. So very clearly 1 and 4 will be more stable than 2 and 3, because in 2 and 3 the stabilization which you will get is because of a resonance, sorry, because in 1 and 4 the stabilization you are getting because of resonance. Resonance means pi electrons get delocalized to stabilize the vacant p orbital. Positive charge means what? Vacant p orbital. So there is a vacant p orbital and there is a p orbital here, there is a p orbital here, and both of them having 1 electron, because of which there is a pi bond. So it goes and overlap with it and they start stabilizing the vacant p orbital by sharing the electrons, right. And now because pi orbitals are loosely held, electrons are more easy to flow around, this is more stabilized. And here you can see, here there is a vacant p orbital, it is being stabilized by so many p orbitals, this p orbital, this p orbital, and this p orbital. So all of them are stabilized by pi bonds. So pi electrons are not strongly held, so they easily overlap very well, the electrons are more easy to move and therefore they stabilize. So very clearly 4 and 1 are more stable than 2 and 3, and among 4 and 1, 1 is more stable than 4, right. Now let us look at 2 and 3. So between 2 and 3, very clearly 3 is more stable. Actually 2 is so unstable, this is not form only. There is a rule what is called as Bridges rule and explains why it does not form. See, when a carbocation is formed, it is sp2 hybridized. There is a vacant p orbital. It is something like this. You are having here, you are having here and here, and you are having p orbital which is perpendicular to the plane. So, if it is sp2 hybridized and so that vacant p orbital is there, the shape has to be planar, trigonal planar. But you can see this molecule, this is a bridged, it cannot become planar, lot of strain is there. So therefore positive charge does not come here, never a pi bond comes on a bridge carbon of such systems, because again for a pi bond to form it has to have p orbital, it has to have p orbital, and p orbital means it should be sp2 hybridized, that means it should be planar and it cannot be planar. So this is highly unstable and this is definitely more stable, 3 is more stable than 2. So the correct order should be, the least stable is 2, so least stable is 2, then it should come 3, then it should come 4, then it should come 1, but I think some problem is there, so that should be the right answer. Let's look at the last question. Yeah, and just last thing, this one is very stable, but definitely less stable than the resonance stabilization. Why is this very stable? Let's look at this also. Thing is, this is a tertiary carbocation. So carbocation is stabilized by positive charge is unstable. Why? Because it is losing electron, it does not have electron, it wants to be neutral. So you know alkyl groups are pumping group, electron donating group. So this pumps electron, this pumps electron, and this pumps electron. So 3 pumping groups are there and they stabilize the carbocation. Apart from that, what happens is there is something called as hyperconjugation. So there is a CH bond. Remember, it happens only with alpha CH bond and not alpha CC bond. So there is alpha CH bond. So the hyperconjugation, what it says, at the alpha position, if there is a sp3 hybridized orbital which has overlapped with s orbital, that means CH very clearly, it very partially, very mildly, it overlaps with the vacant p orbital of the carbocation. So though you can see it's very far, but orbital is kind of cloud, so they overlap very little amount, and therefore because of this overlap it gives certain amount of electron density to this p orbital. So when it gives certain amount of electron density to this p orbital, it becomes stable, and because that it gains stability. So the more number of hyperconjugate structures, more will be the stability. So now see here how many are there? 3 hydrogens are there. This means 3 orbital will overlap. Again here 3 bonds are there, right? 3 CH bonds are there. All of them are hydrogen CH bonds. Sorry. Yeah. So like that 3 plus 3 plus 3, total 9 hyperconjugate structures are there, which makes them very stable. I must have drawn it. Let us look at it once again. Yeah, so this is the one. So this is sp3 hybridized orbital overlapped with s. So CH bond, basically it overlaps with the p orbital here. So this is one, second overlap and the third overlap. Similarly 3 plus 3 plus 3, total 9 hyperconjugate structures. Last question for today's session. Among the dimethyl cyclohexanes, which one can be obtained in enantiomer pure form? So it says these are the dimethyl cyclohexanes which can be obtained in enantiomer pure form. That means it should not have pair of enantiomers, right? So what it says is, for a molecule to be enantiomer pure form, the first criteria is molecule should lack plane of symmetry, right? If a plane of symmetry is there, that means chirality is lost. Okay, then we cannot get pure enantiomer form. So it's difficult to gauge at the symmetry of cyclohexane in chair conformation. We have to make first the planar structure, so it becomes easy to understand, because here no, it's not planar as it looks like. This part is coming out, this part is coming out, this part is coming out, so you understand. So this coming out, very difficult to see the 3 dimensions, much easier to make it in the cyclohexane. So let us look at in the planar form. So you see here the hydrogen is above the plane and this CH3 is below the plane. So what we'll do is hydrogen which is above the plane will make it towards the viewer, okay, and CH3 which is below the plane we are making away from the viewer. On the position on the neighboring carbon, so this position 2 if we take, so this is the one. So here you look here, sorry, uh, yeah, if you look here, hydrogen is down of course very clearly and CH3 is up. So CH3 is above the plane, hydrogen is below the plane. So because CH3 is above the plane, it will be towards the viewer. Look here again, here CH3 is below the plane, this CH3 is below the plane, so we are having both the CH3s away from the viewer. Here position 1, if this is position 1, this is position 2 and this is position 3. So at position 1 and 3 you have to put the both CH3. CH3 is below the plane, CH3 is below the plane. So both of them are away from the viewer. Similarly here 1, 2, 3, 4, 1, 2, 3, 4, CH3 is below the plane, CH3 is above the plane. So away from the viewer towards the viewer. So now we have to look at the plane of symmetry. So only at position A plane of symmetry is not there. Here you just cut it like that. So towards you is hydrogen, this side also when you come it is towards you is hydrogen. Here behind is CH3, behind CH3, everything else is same. Here also if you cut it from the here you can see it is exactly into 2 equal halves. This also is exactly cut into 2 equal halves. So A is the answer because it lacks plane of symmetry, right? So that's the answer. We'll do the rest questions in the next session. Okay, thank you.